All right.
Last part of the session, and the speakers.
All right. Hi. I'm Michael. I'm here to talk about Datafun, which is a language that I and my advisor Neil have discovered/invented, somewhere between the two. So without further ado, I'm going to jump into an example of the kind of problem that Datafun is aimed at solving, and that is static analysis. So here's a program. You can't see all of it. That's fine. You can see the two lines that matter, which is there are two print statements, and I'm going to do a static analysis on this program, and I'm going to show you that this line can be replaced by print 0. But the static analysis will not be able to determine that x is constant, and in fact, x is not going to be constant. So the way I'm going to do this is I'm going to abstractly interpret my program. I'm going to more or less run through it and keep track for every variable at every line. Is this variable not yet defined? Or is it a constant, so far as I know? Or might it take on multiple possible values? And I'm not going to track all the values, because that might take forever. I'm only going to know, is it not yet defined, constant, or varying? So let's go. First line sets x to 0. OK, x is 0, and a constant at that line, so far as I know. Second line sets c to x. Well, x is still 0, so c is going to be 0. Now we're entering a possibly infinite loop. Variables don't change. Print statements don't change variables either, so that was easy. Now we increment x. So now x is 1, c is 0. Am I done? I've run every line in the program. Well, no, I can't be done, because if I was done, my static analysis would say, oh, x is a constant with value 0 at line 5. But of course it's not. As you can see, this is an infinite loop that increments x every time through. So that wouldn't be acceptable. So what we do is we propagate the information from the bottom, line 6, back up towards the loop. And now, previously, x was 0. Now we're saying it becomes 1. Like I said before, if a variable takes on multiple values, I'm just going to say it varies. And I'm going to represent that with the symbol top. Right? So x now takes on multiple different values on line 3. C, on the other hand, is still 0. And the rest of this loop is simple. I just propagate the top, the varying of x, down through the program, because nothing changes it until line 6. And adding 1 to an unknown value is still an unknown value, still a varying value. OK, so now I go around the loop again, but this time nothing changes, right? X was top before, x was unknown before, it's still unknown, c is still 0. Nothing is changing anymore. I've analyzed all that I can in this program, and we're done. And now, look at the values of x and c on lines 4 and 5. Like I said, the static analysis has determined that c is indeed constant on line 4, and we can replace print c with print 0. But x we couldn't determine was a constant, and indeed that's because it isn't in this case. OK, so this is an example of a very general and powerful technique, which is computing fixed points of monotone maps on semilattices which satisfy an ascending chain condition. That's a whole lot of jargon. Let's see what each of those mean by relating it to what we just did. Fixed point. What that means here is we kept going until nothing was changing anymore. Right? We didn't define our static analysis by sort of structural induction on the shape of our program, go over each part, figure out what it does, and build up the answer out of that. Although we did go over our program, we defined it by going over the program possibly multiple times until nothing was changing anymore. Monotonicity here manifests in the fact that we gain information over time. In particular, our model of the value of a variable at a given line only goes in one direction. It goes from saying, well, it's not yet defined at this line, to saying, well, we think it's a constant at this line, to saying, well, actually, it's a variable. We don't know. Right? We never go backwards. Once we've established that x could be either 0 or 1, we never say, actually, no, it's always 0. OK. Semilattices. So I said we always go in one direction. If we order the values that we have our variables abstractly take on by the direction in which we go, we get this picture. Right? Small things, things we start out with at the bottom, things we end up with at the top. And this ordering forms a semilattice, which is to say, has a least value, bottom, not yet defined. And it has, for any two elements, they will have a least upper bound. And this is what we used to combine information about the old and the new execution. So we said x initially had the value 0. Then when we looped around, it got the value 1. The least upper bound of those two is top, meaning it varies. So that's how we used the fact that it's a semilattice. And finally, the ascending chain condition just means you can't keep going up forever, right? If you look at this lattice, you can only go up twice, and then you're all the way at the top, right? And together, this unidirectionality and ascending chain condition mean that our static analysis terminates. You go in one direction, you can't keep going that way forever, eventually you must stop. So this technique is, as I said, very general. Here are a bunch of examples of using this technique, right? Many, many static analyses can be phrased this way. A lot of graph algorithms can also be phrased this way. To my surprise, parsing can even be expressed this way, and we're going to see that as an example later in the talk. And in fact, there already is a language called Datalog that more or less has this as its core idea. And I'm not going to explain Datalog because I don't have enough time, but it allows you, every Datalog program can be expressed as finding a fixed point of a monotone map on a semilattice, where that semilattice in particular is finite sets. So one of the motivations for the present work, for our work on Datafun, is to loosen this restriction and allow considering other semilattices. For example, the one that we just saw, right? That one, that's not finite sets. So I've told you what Datafun is aimed at doing. Now, what does it actually look like? We start with a simply typed lambda calculus. Then we want to talk about ordering, about monotonicity. So we interpret our types as partially ordered sets, some of which will be semilattices. Now, we need to know when functions are monotone, so we know which functions we're allowed to take fixed points of. So we track monotonicity, and we do that via types. And to my knowledge, this is probably the most novel thing about Datafun. I haven't seen any other languages that explicitly track monotonicity using types. If you have, talk to me afterwards. And all of this, of course, is to let us compute these fixed points, right? That's the point. And we want to know they terminate. Datafun is a strongly terminating language. No looping forever. All right, so, and the rest of my talk is going to be going through those bolded things in order. First, I'm going to talk about types as posetsets, then about tracking monotonicity, then about fixed points. So, types as posetsets. The orderings we put on types are mostly what you would expect. The naturals are ordered 0, then 1, then 2, and so forth. Booleans are more or less ordered arbitrarily. False is less than true. This turns out to be useful for various things. Finite sets, these are the workhorse type. Almost all of our fixed points will be at this type or something related to it. And they're ordered by subset, right? One set is less than another if it's a subset of that set. We have two kinds of functions. Ordinary functions, which could do anything, and monotone functions, which respect the order on their argument. Increase the argument, the output also increases or stays the same. And they're ordered pointwise, the usual ordering on functions. You may wonder whether we need both of these, and we do. Here's an example of a function that needs both ordinary functions and monotone functions to express the type of. Member tells you whether the number x is a member of the finite set of numbers s, and it's monotone in the set, right? As you grow the set by adding more elements, it can only go from false to true. But just because 0 is in the set doesn't mean 1 is in the set, right? It pays no respect to the ordering on the x argument. So here's an example of a function mixing monotonicity and non-monotonicity. All right. Now I'm going to talk about actually tracking monotonicity, the sort of heart of this talk. So we have a sort of dual vision, right? We have ordinary, and what I'm going to call these potentially non-monotone functions discrete functions. And then we have monotone functions. Because we have two types of functions, we end up with two kinds of variables, right? A lambda for a discrete function introduces a discrete variable. A lambda for a monotone function introduces a monotone variable. And thus we have two typing contexts, delta for discrete variables, gamma for monotone variables. And this is our typing judgment, which you can gloss as saying E has the type A with free variables in delta and gamma. And moreover, as you increase the variables in gamma, the value of E can only increase. Delta, you don't know. Increase the variable in delta, anything might happen. All right. So I'm not going to go through every typing rule in Datafun, but I'm going to give you a few to give you an example of the flavor. So here's the rule for applying a monotone function. This is perfectly ordinary. It's exactly what you would see in the simply typed lambda calculus, except that you have two contexts. Now, here's the rule for applying a discrete function, and I've highlighted the difference in red. What's going on here is, no matter what the context you started out with when you applied the function, the argument gets an empty monotone context. It may not refer to any monotone variables, right? This is because the function that we're applying to this argument will not respect any ordering on this thing, right? So your argument might increase monotonically, but the function does not care. It will throw that away. Here's an example of what would go wrong if we did not if we did not wipe clean this context. I could write a coercion function that would take any function on the naturals and turn it into a monotone one. That's obvious nonsense. And it would be really simple to write too, right? Coerce fx equals multiply f to x, right? The thing that is disallowed, that makes this not type check, is this rule which wipes clean the monotone context and says you cannot refer to x. X is a monotone variable. You may not use it in the argument to a non-monotone function. Okay, now I'm going to talk about finite sets because they're kind of an important part of the language. We have four ways of constructing finite sets. You have the empty set, you have the union of any two sets, you have singleton sets, and you have this big union which says, you know, for every element x of the first set, I'm going to construct another set and now take the union of all those other sets. And this is a monadic bind operation just for finite sets, very similar to the monadic bind for lists. All the typing rules for these are normal except for the one for singleton sets, which does the very same context clearing thing. And this is because the order of sets is by inclusion. It does not respect the ordering on the elements. The set containing 0 is not a subset of the set containing 1. So you have to do the same thing. And so this sort of context clearing action comes up a lot in Datafun. And if you want to know why, read the paper. But it's not just random. There's an underlying semantic reason for this. I also want to note, as a matter of syntactic sugar, we can add set comprehensions to this language. This is just syntactic sugar. It's the same as adding list comprehensions once you have the list monad. It's very convenient. Here's an example of why it's convenient. Here's a simple function written in Datafun. So bullet composes two finite relations, a relation between A and B, and a relation between B and C. And it's monotone, right? As the relations increase, their composition will increase. And the way we write it, unfortunately, there's a right brace hanging off the end of the slide, but the way we write it is very much how you'd write the mathematical definition of the composition of two relations, right? It's the set of all pairs xz, where xy for some y is in S, and yz is in T. The only difference is we put a bang for the y, and this is us being very explicit and telling Datafun these two y's are the same. Check that they are equal, right? So you can think of this as two nested loops, 1 over S, 1 over T, where it puts a guard saying that y must be equal to that y. Otherwise, don't generate any element for this. And if you're sharp-eyed, you'll see a little subscript, eq, which says we must be able to check the type B for equality. We must be able to ask, are two B's equal? Okay. So now I'm going to talk about fixed points. So fixed points are expressed like this, right? This takes the fixed point of the function lambda x dot e. Here's the typing rule for it, and this involves one thing we have seen and three things that we haven't. So the thing we have seen is monotonicity, right? It puts the variable x into the monotone context to guarantee that the function we're taking the fixed point of is monotone. This is the whole reason why we have this monotone context. So the thing we haven't seen is this notation. So normally I write A, B, C for types. Here I write L subscript fin. What that means is this has to be a semilattice type. And I won't describe how we determine whether something is a semilattice type, but it's pretty simple. It's just a syntactic check. Some types are, sometimes aren't. Has to be a semilattice. Has to be finite. A finite type, only finitely many values of that type. This is our conservative approximation of an ascending chain condition. We could probably loosen this restriction, find other ways of approximating an ascending chain condition, but we haven't needed to yet. And it needs to have equality tests, and this is for implementation reasons. The naive way to compute a fixed point is to iterate from the bottom element, and you need to check that the new value when you do one round of iteration is equal to the old value. If it is, you've reached a fixed point. And there are all sorts of ways to optimize this, but none of them get around the fact that you still need to test equality. So here's an example of using fixed point, right? This is computing reachability in a graph, or transitive closure if you prefer. So I take a set of edges, set of pairs, and I produce a set of pairs representing, x comma y will be in the result if there is a path of one or more edges between x and y. And so the way I say there's a path, if either there's an edge between them, right? So, or there's a path to some intermediate point and then a path from that point on to our final destination, right? So start with a set of edges and start combining things, combining paths that have the same intermediate point. And then once you can combine no more, you're done. You've reached a fixed point and you've found all the paths. And in Datalog, this looks like this. No, this is transitive closure, not reflexive transitive closure, just because it's simpler to put on one slide. You can do reflexive closure too. Okay, so I said we were going to do a parsing example. So there's a very simple algorithm called CYK for parsing arbitrary context-free grammars. So I'm going to write non-terminals with capital letters, literal strings with lowercase letters, and I'm going to assume that all of the rules in my grammar are of the form a non-terminal A produces the concatenation of two other non-terminals, or of the form a non-terminal A produces a literal string. This is called Chomsky normal form, I think. And you can write any context-free grammar in this form. It's just kind of a pain. Then what we're going to do is apply a bunch of inference rules until saturation. And if I've done my job, as soon as I said to saturation, you should have thought fixed point. Because we keep doing it until nothing changes. Those are the inference rules. There are only two of them. It's a really simple algorithm. One of them says what to do about literal strings, the other about concatenation, right? And I'm not going to discuss the details, but that's the algorithm. It's very simple, and it has a very simple translation into Datafun, right? First, we talk about the types we want to operate over. So we represent, we consider only concatenations of two symbols or literal strings. Right? Our grammar is just a set of production rules, like literally a set of production rules, no fancy work involved. And then we have the step function, and this is the function we're going to want to take the fixed point of, right? In fact, these are the facts we're going to derive through inference. And there are two parts to our function, this part and that part. Each part corresponds directly to one of the inference rules I gave before. Each one is just saying, let's look through all the facts we've derived so far and see whether they match the premises of one of these rules. If so, generate the conclusion. And that's it, right? Very simple transcription of the natural inference rule-based algorithm. So, that's what I had to say. The core idea of Datafun is many algorithms are concisely expressed using fixed points of monotone maps on semilattices. Datafun is aimed at expressing these in the most natural way, to me at least, as a functional programmer. You write the function, then you say fix. The key idea that I think is probably the most novel idea here is to track monotonicity using types. We have some stuff I didn't mention here. We have a simple denotational semantics, and we have a prototype implementation. And this, if you know Datalog, this can be seen as a generalization of Datalog to other semilattices with different syntax. There's a link if you want to check it out. And I think that's most of what I wanted to go over. I have other slides I could go over, but I think I should stop for questions.
Phil Wadler, University of Edinburgh. That was very nice. I have several questions here. One is you said it's like Datalog, but for semilattices. So what happens if you just added semilattices as a data type to Datalog? What do you get the difference?
So you don't quite just need to add them as a data type. What you need to do is generalize, Datalog is built on relations, and you need to generalize relations so that they can be thought of as relations valued at a semilattice other than Booleans. Because finite sets can be thought of as Boolean valued relations, so you generalize them to get relations valued at things other than Booleans, and you get somebody else's work, which was presented in PLDI 2016. I don't have a good summary of it, but it's called Flix. I think the title of their paper was From Datafun to Flix, and it's basically an instance of synchronicity. They had a very similar idea to us, but came up with a different syntax based on extending Datalog. There are some differences in our particular approaches. We check monotonicity with types. They don't. They suggest using lightweight verification. We use types to describe semilattices. They say code your own semilattices with Scala. But the same core idea.
We also have higher order functions.
Yeah, right. We have higher order functions that operate over relations. So you can write a function that takes a relation and does something with it. I don't know that they have that.
So that's a big difference.
Yes.
Right. And your initial example, you had this infinite semilattice, and you said, this is one of the cool things we're doing. But then when you gave your fixed point rule, you restricted the semilattice to be finite. So that seemed to go exactly against your motivation.
That's true. So if we were coding up that example, we would need to add an infinite semilattice and slightly generalize our checker. I don't foresee any problems in doing that. It's just a matter of how do you write the thing that checks that your semilattice type has an ascending chain condition.
Hi, Jeremy Gibbons, University of Oxford. Thank you, that was very nice. I just had a query about the pling that you had in your comprehensions. Is that just the same as not having a pling, having a different variable, and having an equality check that follows, or do you do something cleverer than that?
Not having the exclamation mark and having a separate clause that checks the two variables are equal? Yes, it's exactly like that. It's just syntax sugar.
Right, thank you.
Ren Romano from Google, formerly IU. I don't exactly have a question, but I wanted to point out that there's actually an extensive literature on type theory for monotone types, and we should talk afterwards.
Okay, excellent.
John Hughes, Sharpish and Cubic, sorry about that. So in order to implement Datafun efficiently, you need an efficient computation of fixed points. So you want to have some kind of work list algorithm going on in the background. How easy is it to optimize the computation of fixed points in general?
In general, well, that's a hard question. The Datalog literature has lots of ways to optimize this, and we're hoping to port some of those over to Datafun. The one we're currently working on is sort of the very simplest one, which is called semi-naive evaluation, which is to avoid redoing work that you've already done. So you know that when you're computing a fixed point, you're always going to grow. So we want to compute only the difference between iterations. So we think we have a way to do that. And we're going to keep going and keep trying to port over things that other people have already done.
Gleb Pergot from Google. So during last Turing Hack, I have had a long chat with Edward Kmet, and he has been working on what he called propagators, which seems to be very similar to the first part of your talk. Essentially, the monotone functions find semilattices, ACC, and the fourth thing there. So how does this relate?
Well, I think you've basically summed up how it relates. It has a very similar core idea, but I don't know how Kmet is expressing propagators. We have a language that expresses fixed points. It would be very interesting to see connections between this work and that work.
So Edward's library, it was just library in Haskell. So it's purely on the, like you say, execution side of things, I believe.
Okay, so it's possible that we could compile this into propagators. That would be cool.